Hi, I'm going to solve a question I got on my midterm, and I'm going to go quite slowly and explain every single step, all the assumptions I made, and share just my process and my tricks to make sure that my final answer is correct. So the question is, a piston cylinder device initially has a volume of 8 meters cube and contains 2 kilograms of helium at 150 kPa. The gas is now compressed to 4 meters cube, while its pressure is kept constant. Determine the initial and final temperature and the compression work in kilojoules. If the process is carried out in isothermal condition instead, what is the work in kilojoules? And they give us the R value for helium. So what do we need to find? So they want the initial and final temperature for isobaric compression, and they want the work for isothermal compression. So here I broke it down. Isobaric, it sounds like barometer, and that's a tool to calculate air pressure, so you know that it's same pressure. Isothermal, thermal like thermometer, same heat. For isochoric, just remember that one. So first things first, we isolate all the givens for a question because that will dictate how we solve the question. So they gave us initial and final volume, they gave us the mass, the pressure, and the R for helium. Here I gave a recap. Usually during an exam, I will just write down all the givens neatly so I can refer them without having to get lost in this block of text. It saves times and keeps me organized. So to solve this question, we have to make a few assumptions. The first one is that helium is the most ideal of gases. If you don't know that, because they give us the R value, you know that we have to use this equation. But if you don't have this equation, you can also go look in the thermodynamics table, and this column gives you the R value. Usually gases, unless stated otherwise, so helium or air, usually those are all ideal gas problems. So we're going to start by finding T1. So that's before the cylinder is compressed. So with a 8 meters cube volume. So we have our equation, plug in the values. So pressure is 150 kPa, volume is 8 meters cube, the mass 2 kilograms. This is our R value, and our unknown is T1. Once we do the math and solve it, T1 is 288.89 Kelvin. It's important to always use Kelvin degrees for this, otherwise your answer will not work. So now that we have T1, we can cross it off our list. The reason I cross things off our list is to make sure that I answer all the questions and all the information they want, to not lose marks just because I forgot to give an answer. So now to find T2, we'll have to make some more assumptions. So in the problem, they tell us that the pressure is kept constant. It's isobaric condition. So therefore, for the P2, it's going to be the same as P1. It's going to be 150 kPa. The device we're using to compress the gas is a piston cylinder device. So that means that it's a closed system. There's no mass coming into our cylinder, there's no mass coming out. So the mass is going to be constant, and that's going to be 2 kilograms right here. Also, while we compress it, the gas doesn't change. Before we compress it, it's helium, and then after we compress it, it's still helium. So the R value will stay the same. So to find T2, we use PV equals MRT again. And the only thing that really changes to find T2 is the volume, because the pressure hasn't changed, the mass hasn't changed, and the R value hasn't changed. Once you solve for T2, it gives you 144.45 Kelvin. So we have the T2, we can cross that off the list to make sure that we answer everything. Looking at our answers, we have T1 equals 288 and T2 equals 144. Does this make sense? So every time I answer a question, I like to reflect on my answers to make sure I didn't make a mistake and that my answers don't break the laws of physics. So here we have a big piston that has helium in it. Then you compress it to about half its volume. So the gas in a normal everyday kind of situation, the gas would be at much higher pressure and a higher temperature. So the only way to get a smaller volume with the same amount of gas is to lower the pressure by cooling it down and lowering the pressure. So you lower the temperature and the pressure, and that will allow you to shrink the volume. So here the pressure is constant. So to achieve that, we had to remove a bunch of heat. So it makes sense that T2 is smaller than T1. This is written down how I figured it out, but it's important that in your mind it makes sense. If you can't intuit that, then maybe you're less prepared than you should be for your midterm. Now they want to find the compression work. So just like we did with temperature, before we even start thinking about how to solve this problem, I like to make assumptions at what my answer will be. So we started with a piston, right? 8 meters cube. Then we did something to it, and now it's 4 meters cube. So the volume shrank. And work is force times displacement. So here our displacement went from here all the way down to here. So it's negative displacement. Therefore, the work output will be negative, right? If this is negative, this is positive, then this will be negative. The more intuitive way to look at things, this is the way I like to do, like just look at problems, is that if you have a piston that's shrinking, you can't really make it do anything that's useful to you, right? You have to push it down and you have to do something to it for it to shrink. And we're all kind of lazy, so it's bad for us. We can't use it. We have to give in the work, so it's negative work. It's a bad thing. If instead the piston was going up, you could put a weight on it and the piston would push it up, so that would do work for us. So that would be positive work because we're lazy and having something lift weights for us is a good thing. So that's how I look at it. So for the work here, we assume a negative work value. So to calculate the work, we have a few equations. Constant volume, right? If the volume doesn't change, work is force times displacement. If your displacement is 0, your work will be 0. So that's pretty easy. Then we have constant pressure, which is our situation here. It's this one. The work is only dependent on the pressure and the volume. We have constant temperature, which is what we'll use for the second work question. And then there's polytropic, which I won't go into really. These may be on your formula sheet if you're lucky. If not, just learn them. They're very useful. So for the first situation, pressure is kept constant. Isobaric, we're going to use this formula. If you look at the formula list and you're not sure which one to use, this one only has one P, one pressure value. It does not have P1 and P2. So you can assume that during the whole process, P does not change. P is constant because it's just one P. So that's my tip. if you're not sure which formula to use. So the pressure is 150 kPa, volume 1 is 8 meters cubed, volume 2 is 4 meters cubed. Once you plug everything there, you get minus 600 kilojoules. So now that we have an answer, double check our work, think on our results. So negative 600 kilojoules. Does that make sense? Well, to get the piston to shrink to 4 meters cubed, we had to pull out all this heat that was in the piston to keep it at a constant pressure, right? So we had to do all this work on the piston to suck out the heat in order for the pressure to remain constant and the volume to shrink. So a negative work value does make sense. So good job, we answered isothermal situation. So, isobaric condition. So we're going to cross it off our list. So now we're going to solve the isothermal work. So the formula we're going to use is work equals MRT, ln volume 2 over volume 1. One thing that's very important for this formula is that it's derived using the ideal gas law. It has the R in it. So if you're working with anything that's not an ideal gas, do not use this formula. It will not work. Just like before, this formula only has one T in it. So that means that for this process, the T has to be constant for this formula to work. So that's how you know that this is the formula for isothermal conditions. So we have a formula, we plug everything in it. The mass is 2 kilograms. They are, T is what we're, T is, yeah, we're going to come back to that, T1 or T2, and then ln of your volume. While I was writing this exam, it took me a little bit to figure out which T to use. Should we use T1 or T2? Because we calculated two T's, right? T1 and T2. If you think about it, the question asks if the process is carried out in an isothermal situation instead. The word instead here is quite important, right? Because when we solved for the temperature, we had T1, and then we shrank it at constant pressure to T2. If instead we're doing this isothermally, T2 doesn't exist because we haven't done that process yet. Therefore, the only option that we have left is T1. Yep, this is what I just explained. So once we plug in T1 here and we do all our math, we get a work output of 800 minus 831. So now that we have an answer, we check, does the negative work make sense to us? So just like before, we're doing work on the piston and it's bad for us because we're lazy. So a negative value is what we expected. Again, work is force times displacement. We have a negative displacement, so that's another way to look at it. But either way, a negative answer makes sense to us. So now we check it off our list. So everything is answered. All our values pass the common sense test. Everything works. Hopefully this makes sense to you and helps you out a bit. Good luck on your exam. Bye.